All right, so now we need to bring up this idea of integration with these multivariable functions. And so we need to review some of the things we did back in Calc 1 when we did single variable integration, and then that'll lead us into this multivariable integration. So remember a couple of things that happened back in Calc 1. So we want to find the area under the curve. We did that by a series of rectangles. We add all these rectangles up. That would give us an estimate of the area. We then go from an estimate of the area to the actual area by using a limit and letting delta x go to 0. And then that essentially is the definition for our definite integral. And that would give us the area under the curve. Now, a couple things. One, not every definite integral does have to represent area. Okay? We use this area concept as a geometric visualization of what's happening in some of our integration to make more sense of it, but not every single integral actually represents area. We have to, sometimes we have a single integral that the answer is negative, and if that's negative, there's no way that could represent area. But we can make every integral eventually describe what's happening in an area. All right. A couple of things in terms of the details. What do we do? Well, what we do first is we take our interval that we're integrating over, and it's a single interval, and we subdivide it up, and that gives us the width of the rectangles. The width of the rectangles is calculated by this delta x value, and we need the height of the rectangle, and that's calculated by the function value. So delta x times the function value, that's the area of a rectangle. We then add all those areas up, and that gives us the estimate for what the area is. The key how we go from estimate to actual area is through this limit. And we do the limit as n goes to infinity. N is the number of subdivisions we made, okay? And it's based off of how we find the width of the rectangle itself. But if we let the number of subdivisions or the number of rectangles themselves go to infinity, our estimate becomes an actual area. And that's the definition for a definite integral. Now, this is how you originally defined what a definite integral was in single variable calculus. And then you learned how to actually do this definite integral in a lot quicker, easier fashion with the fundamental theorem of calculus. And so you basically did it through antiderivatives. But this was the initial definition of a definite integral. And so all this picture right here, this should make sense in terms of what you know about definite integration and area and how they're related. So then what we want to do is we want to think about this in a multivariable scenario. And so what we think about is we have a multivariable function. That would be a surface. We want to integrate that over some interval. But the problem is it's not a single interval. Our domain is based off of x's and y's. And so we would have an interval on both the x-axis and the y-axis. So if we have an interval on the x-axis, say a to b, and an interval on the y-axis, say c to d, what it does is it grids off, essentially, these two separate intervals. It grids off an area, a rectangle, in the xy plane that we're going to integrate some function over. This would be the surface or the function that we're integrating over that interval. And what we can do is to geometrically represent what's happening here is we can think about the volume in between the two. So here's the area, here's the surface, find the volume in between. Very similar to here's the function, here's the interval, find the area in between. Okay, so we look at this interval, we'd have to subdivide that interval up. So we subdivide the x interval up the exact same way. We subdivide the y interval up in very similar fashion. And what we get is we basically get this grid under here. Each one of these little squares in this grid would be the base of what we're going to call a rectangular prism. So the area of that base should be delta x times delta y, the width along the x-axis subdivision and the width along the y-axis. So if I pull it out here, this would be delta x, this would be delta y. The width in the y direction, the width in the x direction. Again, this width in the x direction, this delta x, is the width of the rectangle that we would dealt with back in Calc 1. We just have another one here creating this square. So this is the area of the base of our prism. And then we're going to take that area and we're going to raise it up to the surface. Okay? We're going to raise it up to the surface. Whether we raise this corner or this corner or this corner or this corner or even the middle, it doesn't really matter how we get to the surface. But we're going to raise this up to the surface and then we're going to get the height of our prism. Well, that's some function value. We're going to take some function value in this square and we're going to raise it up to the surface. And if I multiply that function value times the area of the base, that'll give me the volume of one of these prisms. Okay? Then what I want to do is I'm going to look at all the prisms. And I want to add them all up. So then I'm going to add up all my prisms. So again, here's the area of the base based off our subdivisions of our x's and our y's. Then I multiply the area of the base times the height, which is some function value over top of that base. So wherever I hit the surface over top of that base, that's how high I'm going to go. That right there will give me the volume of one of those prisms. I then add all those prisms up in this picture, and that should give me an estimate of, again, the volume between this base and this surface. So that volume all in there, all that space in there. That should be an estimate. But I don't want an estimate. I want to find the actual volume. So what I'm going to do is I'm going to then do the limit as the number of subdivisions goes to infinity. So if I take the limit as the number of subdivisions goes to infinity, okay? So I subdivide the x-axis even faster, I subdivide the y-axis even faster, smaller grids, smaller areas of my bases and my prisms. I can fit more prisms into my picture. My error then goes down to 0. What I get is essentially the actual volume. And what I can say is, well, that should be equivalent to what we call a double integral. And so that's the definition of a double integral. So if this limit, as n goes to infinity, of the sum of f of x times delta x was the definition of a single integral from a to b of f of x dx, what I'm saying is then this limit, as n goes to infinity, of the sum of the function of two variables times delta x times delta y, okay, should be the definition of a double integral of f of x, y dx. And that's exactly what this is. So this is the definition. You see the correlation between what you had in Calc 1 and what we have now. This summation here and this summation here, the difference is we added an extra variable, and what that adds is an extra integration. How we go about actually doing what we call a double integral, we have to learn it next, but you hopefully see the transition from one to the other. So let's just go through the definition. If f is defined on a closed interval, a closed bounded region, which is really two intervals on the xy plane, then the double integral of f over r, that region, is given by the limit as n goes to infinity of the sum of f of x, y times delta x. Basically add up all those rectangular prisms and let the number of prisms go to infinity. And that's provided that this limit can exist, but limits sometimes don't. But that's the definition for the double integral. Okay? Just like I said, not every single integral represents area. Not every double integral is going to represent volume. There's some things that you have to worry about. Your function has to be greater than or equal to 0 over the region for the double integral to actually represent volume. Some things you learned in Calc 1. I'll just go over it real quick. Get rid of this. So you had your x-axis. Your function had to be above the x-axis. So your function had to be positive. The y value had to be positive so that you can talk about this area. If you had this scenario where here's the x-axis, okay, and your function was down here, and you tried to find the integral over this, the area over this integral, area over this interval, you couldn't simply just do the integral of the function, right? They had to worry about, oh, this function's negative now, so I have to make some corrections. So the same thing goes here. Here's the xy plane. Here's the z-axis. Our function, our surface, has to be above the xy plane, above this region, for me to find the area, or the volume, I should say, in between. If my surface is below the xy plane and I want to find the volume, I would have to make some corrections. And typically all you have to do is multiply your function by a negative to correct the fact that the heights of the rectangles, or in this case the heights of the prisms, are calculated in a positive fashion. But just to reiterate, not every single integral initially represents area, not every double integral initially represents volume, but we can make them work out if we make some corrections in our computation. So now how do we actually do a double integral? So we do it by essentially what we call an iterated integral. An iterated integral is basically telling you when you do a double integral, you don't do two integrals simultaneously. You do one at a time. So we do a single integral, and then we integrate that single integral again. And so if I had a double integral here, where I had two intervals, one on the x-axis, one on the y, and you can see which one is which by which one is attached to the dy and the dx. Okay? So here inside the parentheses, you have the interval on the y-axis with respect to y. I could do that integration. Then I could integrate the next one when I get the answer to this. So do one at a time. I could also reverse the order and do the x integration first and then the y integration second. Either way, as long as it matches up, the y and the x's, keep your intervals and your variable you're integrating with respect to consistent. You do one at a time, and once you complete those two integrations, one followed by the other, you can get your answer. And you might say, well, you know, what's the purpose of this? Well, this is just essentially now attaching our previous definition of what a double integral is to iterated integrals. So this double integral is essentially a iterated integral. So let's see an example. I think this will clear it up much better. So here we go. We want to evaluate this function over this region in the xy plane. So if you were to look at this in the x-axis, we're between -1 and 2, and then the y-axis between -2 and 1. That's going to create some rectangle for the x-axis and for the y-axis, and we could grid that off, and that's going to be the base. And so the idea here is, in order to do this double integral, we need to do both of these intervals. In this case, the order doesn't matter. We can integrate with respect to x first or y first. And this is because our x and our y variables are each between constants. So the interval on the x-axis is between two constants. The interval on the y-axis is between two constants. So since we're between constants on both the x and the y-axis, we have this nice neat grid. And the order isn't going to matter. Whether we integrate with respect to x first or y first isn't going to make a difference. Eventually that will change, because our area that we're integrating over, the region that we're integrating over, is not going to be as nice and neat as a rectangle all the time. But we'll get there. So when I do this, I say, all right, well, looking at this function, I'm going to have to integrate with respect to x and y. Which one's easier to do first? If there is one, I choose that one first. In this case, it doesn't seem to matter, so let's just say we're going to integrate with respect to x first and then y second. So then that means the innermost interval would have to be the x interval, so -1 to 2, so that's my x interval. And the outermost one will have to be my y, so -2 to 1. So the way I do this is I just do one integral at a time. So -2 to 1 is just going to sit there. That's my y interval. I'm going to do this -1 to 2, x squared minus y squared, dx first, and then I'll deal with the dy second. So I got to integrate with respect to x. How do I do that? Well, I do it the same way I did derivatives. I'm doing derivatives backwards, right? That's what integration is all about. So you're going to treat x as the variable, and y is going to be treated like a constant. For integration, we have our constant multiple rules and how we deal with constants, and we'll do the same thing here. And so when we do this, x squared with respect to x is going to be x cubed over 3 minus y squared with respect to x. Well, that's a constant. Integral of a constant should be that constant times x. We could still use the sum and difference rules and the power rules. All the rules are the same. We're just now using y as a constant when we're integrating with respect to x. All right. So then I'll plug in 2 and I'll plug in -1 for x. Right? Remember, these are x values. This is all on the x-axis. We haven't dealt with y yet. And so we still have this -2 to 1 sitting here. So if I plug in 2, I'm going to get what? 8 over 3 minus 2y squared. I'm then going to plug in -1 and then subtract it. So I'm going to get minus -1 will give me -1/3 minus becomes plus y squared dy. And I'll simplify this before I deal with y, but then I have this integral -2 to 1 of 8/3. This will be plus 1/3, so 9/3, so it's 3. And then -2y squared minus another y squared is -3y squared dy. So that's where I am now. Now it's time to deal with y. But notice, it's a single variable integral with just y's in it. This is simple. This is back to Calc 1. So you would get 3y minus y cubed between -2 and 1. Plug those in, you're going to get 3 minus 1 minus, -6 plus 8. So in the end, what do I get? 3 minus 1 is 4. This is going to give me 2. 4 minus 2 is 2. There's my answer. There was no volume, calculate the volume problem here. It's just evaluate the double integral. And we do it using our basic ways of integration. What we learned in Calc 1. What we learned throughout partial derivatives in Calc 3. And just thinking about that in reverse. When you integrate with respect to x, you treat y like a constant. Integrate with respect to y, you treat x like a constant. When it comes to constants and integration, you have the constant multiple rule. You have the integral of a constant itself, and should be no problem. Let's do another example. Let's do this double integral over this integral. Notice x is again between two constants, y is between two constants. Sometimes they give you this interval like this. All right. They just write it in interval notation with an x in between, so this cross this. I'm not as huge a fan of that notation because it doesn't necessarily denote which one's the x and which one's the y. You just assume that the first one is x and the second one is your y interval. When they write it in inequality notation, it's clear, okay, this is the interval for x, this is the interval for y. So I prefer that, but you'll see both, so it's not a big deal. All right, so again, integrate with respect to x or y, since they were integrating over this box right here, this rectangle, where the x's go between -2 and 3, and the y's go between 1 and 4. We create this little box, grid that off. That's the integral. That's the area we're integrating over. Order is not going to matter, right? Everything's a constant. It's a nice, neat square or rectangular box. The function, it doesn't really seem like if I integrated with respect to x or y first would make really much of a difference. We did the last one with respect to x. Let's do this one with respect to y. So let's do dy and then dx. Okay? So that would put 1 to 4 on the inside and -2 to 3 on the outside. All right. So that being said, let's worry about the -2 to 3 later. Let's just do the integral from 1 to 4 of 2x plus 3y squared with respect to y, and then we'll deal with the x again later. So if we're integrating with respect to y, it's a sum, right? I can integrate this piece separate from this piece. This with respect to y, there are no y's, so this is one giant constant. So, So I would have 2xy plus this with respect to y would give me y cubed. And then I have to evaluate between 1 and 4. Now you just got to remember that these are y's. This is going to go in for y, and this is going to go in for y. If you think you're going to mess that up, just put y here. Y equals 4, y equals 1. So remember, these are y values. We haven't dealt with the x's yet, which are here. Okay? So, what do we get? Well, we still have this integral sitting here. We haven't dealt with it yet. We have plugged the 4 in for y. It's going to give us, what, 8x plus 4 cubed. What's that? 16 times 4, 64. Minus, plug in the 1. You're going to get, what, 2x and 1. It's being subtracted because of the way your integration works. All right, so then is this integral? I'll simplify it before I integrate. So I really would have negative 2 to 3. 8x minus 2x gives me 6x. 64 minus 1 gives me 63. So what am I going to do? Integrate with respect to x? Well, this is easy now, right? I just have one variable in here. I'm integrating with respect to that variable. This is the interval for that variable. Everything matches up. So it's basically back to calc 1. So what's this going to be? 6x squared over 2, so 3x squared minus 63x between negative 2 and 3. Plug those values in. I'm going to get, what, 9 times 3 is 27 minus 63 times 3. Then I plug in the negative 2, so I'm going to get 412 minus 63 times 2. So overall, what do I end up with? So it looks like I get negative 327, which is fine. I got a negative answer. The question didn't say find the volume based off of this double integral. Just to evaluate the double integral in this case. I got a negative answer. Totally fine. We'll worry about volume in a minute. If the question dictates that you need to find volume, there's some things you got to watch out for. But in this case, do the double integral. You see, double integrals are really not that much harder than single integrals. You're just doing two of them, okay, one at a time. As long as you keep track of what variable you're working with, you keep the intervals straight so the y interval matches up with the x interval matches up. You integrate with respect to one variable, you hold the other constant. It shouldn't be much of a problem here with these double integrals. So now we have a volume question. So we want to find the volume between this function and the rectangle 0, 3, and 0 to 1. So this is your x, this is your y. So our x-axis were between 0 and 3. Our y-axis were between 0 and 1. So this is the rectangle we're integrating over, so we would grid that off. Okay. The surface, which is this surface over top of that, looks like this surface right here. If you notice, this function is completely above, look at the z values. The z values go from 0 to 15. It's completely above the axis. Okay, it's completely above the xy plane over that grid, over that rectangle, based off of this. So I have, I'll draw it just randomly. I have a area in the xy plane. My surface sits completely above that area here, and I want to find the volume in between. Okay, so I want to find the volume in between the two of these and the space in. So everything sets up nicely. If I had an issue where I had my area in the xy plane and my surface, let's say below the xy plane here, and I want to find the volume in between, that would be a little bit more of an issue. I would have to make some corrections. Or let's say some of my surface was above and then it kind of went downward, and then below it was a little bit here. Then we'd have some issues. For right now, we really can't do a lot of that. We can deal with the one scenario where we have the entire function is below that, and we want to find the volume in between. We can do that by saying, all right, well, if here's the function, we want the heights of our prisms really to be measured in a positive fashion. Well, if we just multiply the function by a negative, that then fixes it. Because remember, the function values down here, these are the z's. The z's down below the xy plane, these are all negative z values. And so we want to make sure that these z values, what we're using as the heights of the prism, are measured in a positive fashion. So if these z's are already negative and then we multiply by negative, now they're positive. And so we just take the whole function and multiply by negative, we're good. This is the same thing we would have done in Calc 1 when our function was down here. We wanted to find this area. This was our function. We would just multiply the function by negative, and ultimately what it does is it kind of reflects it up. So now you're looking at this picture. Well, by multiplying the function by negative, you're essentially pulling it up, okay? And now the surface is up here. Now we're finding the volume in between. We don't have that issue here, though. That's the good thing. And you can see that through my little picture I put here for you. But you can also see it just by thinking about these are the x's and these are the y's I'm working with. In order for this to be negative, in order for this to be a negative function value or a negative z, we would have to get this whole thing, at least this piece, to go below 16 so that we can get 16 minus something bigger than 16 and get a negative. Well, if x is going to range from 0 to 3, the biggest this will get will be 9. And if y ranges from 0 to 1, the biggest that will be 1 times 3 would be 3. So I'm going to get 16 minus 9 minus 3 is going to give me 16 minus 12, so 4. So even with these x's and these y's, I'm never going to get outside of 4 as my smallest function value. So the smallest function value would be 4, which would be back here in this along this edge here. So right here is probably where it's going to be the smallest. All right. So everything's good in this case. So if I want to do the volume, I can simply do the double integral of this function with respect to the area. The area is based off of the area I'm integrating over. This is the function itself. No corrections need to be made. Everything should work out. Our double integral should relate to a positive value, and that positive value would represent the volume in between here. Okay, the volume in between this box. Where this is the top, and the rectangle based off of this is the base. Doesn't matter whether I do x or y first, they're constants. So in this one, it doesn't look any easier. What did we do? Last one we did y, so let's do x first this time. So I have 16 minus x squared minus 3y squared. Let's do x, then y. X was 0 to 3, y was 0 to 1. So what am I going to get? The 0 to 1 is just going to sit here. I'm going to integrate this with respect to x. So I'm going to get 16x minus x cubed over 3 minus 3xy squared. Right? This is a constant. And with respect to x, it should be that constant times x when you integrate it. So 3xy squared. Between 0 and 3, the dy is going to sit here. And so 0 to 1, plug in the 3, I get 16 times 3 times 3 minus 27 over 3 is 9. Plug this in here, I get minus 9y squared. If I plug 0 in here, here, and here, they're all going to be 0, so I'm not going to have that. So now this is the integral I want to do. Well, I have to do 16 times 3 minus 9, so I can simplify that constant a little bit. Then I'll do it. I mean, I could leave them separate, but 39 is what we're going to get there. So I have the integral from 0 to 1 of 39 minus 9y squared dy. And so that's easy. 39y minus, 3y cubed between 0 and 1. So it's going to give me 39 minus 3. Plug in 0, I get 0, so 36. So my volume is units cubed, whatever the units are. I don't know what the units are, but it's a cubic measurement. But that's my volume. So if I was thinking of this surface over this rectangle, which sits right here, and the volume in between, that volume should be 36 units cubed. Here's a nice little trick we can use sometimes to help speed things up. It doesn't work a lot, but when it does work, it is very helpful. One thing I see students make a mistake on a lot with these double integrals is the concept of treating one variable like a constant while you're integrating with respect to another variable. What this little trick does is help to eliminate some of the issues there. All right, so here we go. When a function is a product of two single variables, so we're looking at this function of x and y, and really that function of x and y is a function of x times a function of y. Overall, that's one giant function of x and y, but if in particular it looks like that, and we want to do the double integral over the rectangular region. One caveat to this trick is it only works if you're integrating over a rectangular region, which isn't going to happen all the time. We'll talk about that in the next lesson. But if we have those two things, that the function is really a function of x times a function of y, two single variable functions multiplied together, and you're integrating over a rectangle where x and y are both between constants, then if we wanted to do that double integral, we really could do it with a series of two single integrals multiplied together. I could do the integral with respect to x over the x interval, the integral with respect to y over the y interval, and then multiply the two answers together, thus kind of eliminating the treating one variable like a constant while I integrate with respect to the other. Now, why does this work? Well, it works because of the way you would do it. If I integrate with respect to x first, this whole thing is one giant constant multiple in terms of this whole function. And so constant multiples can be pulled out. And so this would be h of y times the integral of g of x dx and then dy, right? So I'd just be doing this integral. And then I'm doing it over an interval from a to b. And so I'm integrating with respect to x, I'm plugging these values in for x. This ends up being a constant. So then what I end up with is that constant, we'll call that c, times h of y dy. In which case I'm just integrating this over the y interval with respect to y, and this constant multiple can come out, which was the answer I got for this integral. So I would just be pulling the constant multiple out, which is this function or this function anyway. So let's just completely separate them, is what this is saying. It's a nice little trick when you can use it. It helps to eliminate that issue of treating one variable like a constant. And so here's an example. This function I could write as 1 over x plus 1 times y. So you see I have a function of x and a function of y multiplied together. The intervals are between constants, so it makes a nice neat rectangle. X is between 0 and 2, so there's my x, 0 to 2. My y goes from 0 to 4. I got this nice neat rectangle I can grid off. Okay. So if I'm going to do this double integral over this area, I can do it by saying, let me do the integral of 1 over x plus 1 with respect to x over the x interval times the integral of y with respect to y over the y interval. This function and this function completely pulled apart from each other. In which case, if I do this first integral, I would get the natural log of x plus 1 between 0 and 2 times the other one would be y squared over 2 between 0 and 4. So if I plug 2 in here, I get natural log of 3. If I plug 0 in here, I get natural log of 1. So I get natural log of 3 minus natural log of 1, which is already 0, times, plug 4 in here, which is going to give me 16 over 2, so 8. Plug 0 in, I'm going to get 0. And so I get 8 natural log of 3 as my answer. Pretty quick. I mean, it makes things go a lot faster by thinking, oh, single integral, single integral. I don't have to say, oh, let me integrate this with respect to x, but treat y like a constant, and then how am I going to do that, and then possibly mess that up. And I see students do that. They mess that up by, the whole treating the variable as a constant is a simple trick of the brain, and you don't necessarily do it the way you're supposed to. So by separating them, we can. But remember, it only works in this very specific scenario. The function you're integrating is a function of two single variable functions multiplied together, and the interval is a nice, neat rectangle. If you don't have both of those things, this no longer works. So x has to be between constants, y has to be between constants, and this function has to be able to be pulled apart as two single variable functions. If all that works, then do your two separate single integrals, y with all the y's, x with all the x's, and multiply the answers together, and you get the answer for the whole thing. You don't have to use this, but it does come up pretty handy.